All right, I apologize. My camera was dying, so I had to plug it in. All right, so I didn't realize that I was going to lose some of this. So anyway, all right, so we have on 4, it says consider the repeating decimal negative 2.1212121212. Let x represent the repeating digits, right, which is 0.121212, and these will go on forever. Then it says multiply both sides of the equation in part A by 100 to get an equivalent equation. And so what I've done is I've multiplied x by 100, and I've multiplied 0.21212 by 100. And then I'm going to write this with the same number of repeating digits. And the reason I'm doing that is because of part C. It says subtract the equations in parts A and part B so the repeating digits cancel each other out. So in order for that to happen, I'll have to have the same number of repeating digits here and here. So I'm going to subtract these two equations. So 100x is equal to 12.121212. From that, I'm going to subtract x equals, and I'm going to subtract 0.121212 so that my decimals cancel out. And what I'm left with is 100x minus 1x, which is 99x, equals 12. And then it says use your answer from part C to rewrite this number. Is it rational? So I would divide both sides by 99. Divide by 99, and I get that x equals 12 over 99. And so my original, which was negative 2.1212, so 12 divided by 99 is right here, 0.121212. So my original number would be negative 2 and 12 over 99. And this is indeed a rational number because it can be written as a fraction. All right, the positive number 0.12345 is a decimal that uses all possible positive integers for its digits. Is this number a repeating decimal? Explain. So it uses all possible positive integers for its digits. So meaning it's going to go 0.123456789, and therefore there's no repeating, since it will be 0.123456789 and so on. This is an irrational number since it will go on forever. And it uses all possible positive integers for its digits. So for example, the next one would be 10, 11, 12, ... So explain why it's irrational. This number neither repeats nor terminates. So in order to be rational, the number must be able to be written as a fraction. Therefore, it will either repeat, as we saw in number 4, or it will terminate, as we saw, for example, in this problem, number 3. Okay, since it does neither of those, it is going to be an irrational number. Okay, let's flip it over to the next side. All right, show, this is the check your understanding. So at this point, you should pause the video. I'm not going to pause here, so please click pause and come back. So it says show that 30.11111 is a rational number. So number 6, 30 0.1111. We're going to show that's a rational number. We're going to do the same thing that we did before. We're going to let x equal 0.1111. We're going to multiply both sides by 100. So I'll get 100x equals 11.1111. Again, having the same number of digits. And then I'll subtract. So I'll have 100x equals 11.1111 minus x, and then subtract 0.1111. My 0.111s will cancel. I get 99x equals 11. I'll divide both sides by 99. I get 11 over 99. You can verify that 11 divided by 99 is indeed 0.1111, repeating. So we can rewrite this as 30 and 11/99, which is a rational number. All right, number 7, we're going to do the same thing. Show that negative 1.808 is a rational number. So we're going to say that x is equal, well, in this case, since it's not going on forever, we're going to do the first method. So this is like from number 4. This one will be like from number 3. I want to multiply negative 1.808 over 1 by some value that will cause this to be a whole number in the numerator. So I'll multiply by 1,000, since I'm in the 1,000s place. So I'll multiply by 1,000 to both the top and bottom. And 1.808 times 1,000 is 1808. So I get 1808 over 1,000, which are both rational. Therefore, which are both integers. Therefore, it's a rational number. All right, next, number 8 is 1.232232223 a rational number, and this goes on forever. All right, so do you see that if I was going to apply this method, my number here terminates? That's why I could multiply by a value that would make this an integer value. I can't do this here because this number goes on forever. If I were to try to apply this method, do you see that these numbers, there's no repeating decimals? Therefore, I can't do this. So since the number neither terminates, meaning ends, nor repeats, it is irrational. And finally, number 9, it says create a 2-digit number XX, but do not use 0 for both digits. So show that the decimal 1.XX is rational. All right, so I'm going to create my XX. This is number 9. XX is going to equal, in my case, I'm going to make it be 33. So I'm going to show that the decimal is 1.33. Repeating is rational. So to do that, I'm going to apply this same method. I'm going to let x equal 0.33. And then I'm going to let multiply both sides by 100. So I'll have 100x equals 33.33, and then I'll subtract them. So I'll have 100x equals 33.33. I'll subtract x. I'll subtract 0.33. I'll get 99x equals 33. Divide by 99, and I'll get that x equals 33 over 99. And so this number would be 1 plus 33 over 99, which is 1 and 33/99, which is, I can also simplify this, 1 and 1/3. All right, let's move along to the next one, number 10. So do you see they did a Venn diagram of that same group of numbers? I did that with using a box. I prefer the box. All right, but here is their representation, and here's mine, right? So there's the same thing. It says a radical sign can be used to write a square root. The square root of 2 is written as radical 2 and has a value of such that when we square it, we get 2 back. A number is called a perfect square if it is the square of a positive integer. The first 5 perfect squares are, there's 1 squared, 2 squared, 3 squared, 4 squared, and 5 squared. Is the square root of 25 rational or irrational? Explain. So the square root of 25 is equal to the square root of 5 squared, which is equal to 5. Therefore, it is rational, right? And I'll explain. Rational, well, 5 is a whole number, which is inside the rational numbers, so it's rational. So since it's a whole number, it is a rational. Next, it says, use a calculator to find the square root of 2. All right, so on my calculator, the square root of 2 is 1.4142135, and it doesn't terminate here. They just can't show me any more digits. And so, does it appear that the square root of 2 is a rational number? No. There is no repeat or terminating decimal. Therefore, so it is irrational. It says, find the value of the square root of 2 minus the value of your calculator displayed in part A. What does the difference imply? So if you take 1.414213562, right, and I'm going to take that, and it says the square root of 2 minus that value. So I'm going to take second function, square root 2, and I'm going to subtract out this value. So minus 1.414213562. And I get a small difference here, right? So I'm going to subtract the square root of 2, or sorry, this from the square root of 2, and I get, this means e to the negative 10th power, which means I'm going to move my decimal 10 places that direction. So it's 0.0000, I have 9 zeros, 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros, 3, 7, 3, 1. There is a difference between the two, so that implies that square root 2 is not rational. Otherwise, when I subtracted these two values, this would have been the entire value of square root 2, which I already knew it was not. Okay, on number 12, we're just identifying, is each number rational or irrational? So is the square root of 1 a perfect square? So yes, it is. The square root of 1 is, right, 1 squared, which is the radical and the root reduce out their inverses, which is 1. So this will be rational. I already know this is irrational. It's not a perfect square. Same thing here. This is irrational because 3 is not a perfect square. Here, the square root of 4 can be rewritten as 2 squared, and a square root and a radical are inverses, and so we get 2. So this is a rational number. 5 is irrational. It's not a perfect square. 6 is irrational. It's not a perfect square. 7 is irrational. It's not a perfect square. 8, you can simplify this square root to 4 and 2 and get 2 square root 2, but 2 is still an irrational number, so this is irrational. And then this would be the square root of 3 squared, and a square root will reduce, and so we get 3, which is a rational number. I know I did those really quickly, so you might want to watch them a second time. All right, moving on, we're going to turn over to page 21. Page 21, it says to check your understanding. Tell whether each type of positive number is sometimes, always, or never a rational number. Explain your reasoning. I'm actually going to go back and look at my picture that I drew. So, sometimes, always, or never, integers. Integers are under the umbrella of the rationals. So these are always rational. Fractions. Well, fractions, we saw that that fractions are always a ratio of an integer to an integer, so fractions are always rational. Square roots of integers. Well, sometimes, for example, I'm going to add this in here, like the square root of 49. Well, the square root of 49 is 7, right? The square root of 49 is 7, so that would actually be down here in the natural numbers, 7. It's here in the whole numbers. It's also here in the integers, and it's in the rationals. So it is a rational, but sometimes, like the square root of 5, is irrational, so we're going to say sometimes. Terminating decimals. Terminating decimals are decimals like 1.25, right? Those were rational numbers, rational, because we could multiply the top and bottom by, say, 100 or 1,000, and this would become 125 over 100, which is rational. And then non-terminating decimals, well, that depends. Here's an example of a non-terminating decimal, but here's also an example of a non-terminating decimal, so that's going to be a sometimes. All right, I hope you enjoyed notes 2-1. I know they were a lot faster than in the past. Have a great day.